session, and we should start with each team introduce yourself. And let's start with the reporter today.
Hello everyone, we're Team Tesla from Kinzhong High School, and this is Jinsan, Guojun, Guohao, and Luoji.
And opponent.
Good morning everyone, this is Team No Niners, and we have No Niners. We have Richard, Thomas, Cedric, and Sarah.
Who are you?
His name is Alex.
Team captain.
我们是那个9120队，然后我们是新竹实验高中的高一，然后就是力学硬核，然后顶离长庚，然后就是中影。
Let's have a welcome everyone, and let's have Julie introduce themselves also. Let's start with on the Reynolds.
My name is Yewang Xu. I'm from National Donghua University.
I'm Ivan Liu from National Yang University.
蔡尚芳，台湾大学物理。
我叫陈宏宇，是师大物理系。
我叫夏平，我是那个原分所，中研院原分所。So I think it's time to select the question, right?
Okay.
Turn.
So opponent
turn.
The opponent challenges number 3, ring on the rock.
Three.
Yeah. We are set.
不是，他是看那些工作人员在哪里。哦，不是他，在这里，我才发现，这个工作，因为我刚刚进来的时候，是有这个这个位置，行业前面挺多的，什么？这个朋友有问题。那你看他未来的法律是怎么？给他就是看他们才会拿回。我后来是每个都进去了，是做满的。哦，对呀，那个出来等于吃完之后那个会高。
我是杨根。
The left one, the mouse point one.
Wait, let me check.
Thank you.
Sure. You said check.
他的名字是有个业绩的，就是我名字可以点，我觉得太早。
为什么我的灰色？就是代表说你可能已经就是出场过很多次。
只是我是出场3次 reporter 啊。
对，那个 reporter 上线3次。
我不能当 reviewer 嘛，就是如果我当 reviewer，可以吧？
应该是不行，因为我记得是出场是有限。
那我还可以当那我还可以当 opponent 吗？
我记得是 report 是不能超过5分。
对，然后
oppose 跟 review 都要是。
好，那我去确认一下。
因为我们上 opponent 跟 reviewer 是同一个人，所以我们继续说。
好，所以是 reporter 3次，然后然后我们要做 review。OK， 好，我们去确认一下。
对，他可以3次都，对。 跟这是同篇的，他有一个上面有一个
这是从剧场，
就是如果今天三个角色都是有可能，这两个是
对，A 就是在这一场这样子。就是说，他如果当下一场他就不能当，对，下一场就是你，就是他等于是下午比赛的话。
你的对手不一样。对，就是看你们不容易选择有这个问题。
Yeah, true.
好，知道。
可以，然后我们要
但是那宝宝没背。
上海支付宝是
And this is our presentation of the ring and rod, and we are Team Tesla from National University High School. Okay, so here's the task of the ring and rod. So a washer on the vertical steel rod may start spinning instead of simply slowing down. We want to study the motion of the washer and investigate what determines the terminal velocity. Okay, here's the observation of the phenomenon, and here's our experiment setup. So we have to discuss about what affects the terminal velocity, and it's the motion state. Okay, so our experimental materials have a bracket and rod and ring. So each of these are balances. So here's the relevant parameters. So if a ring which mass is n, and inner radius r, and outer radius r2, thickness is e. And a material of stainless steel and water friction, and also copper. And our radius is r. So we can define the inner radius and the outer radius, and the challenges about the thickness of the rod. And here's our setup. So we have 7 kinds of rings from A to G, and our mass is from 55 to 35.8 to 16.4, to 11.5 to 6.4 to 4 to 2.3. So different rings will pair to different rods. So 4 and 7, so have 28 consequences. So the radius of the rod 1 is 0.75, and the second one is 0.65. The third one is 0.25, and the fourth one is 0.2. So 1, 2, and 4 stand still, and the third one is copper. And so after our experiment, our best curve is defined on the 3F experiment. So here's the first and second. And since we cannot control about the force we gave to make the washer spin, so we have 2 and 3 different kinds of experiments. So the 2 curves are the 2 phenomena of different forces from hand. So as we can see in the xt squared, so the slope doesn't change, and the slopes of 2 curves are the same. So we can get that the force wouldn't affect the terminal velocity. So here are two different stages we've got. So the first stage which slows down and only contacts at 1 point. And the second stage we have a steady velocity and contact at 2 points. So it's about the first point. So the first stage will be faster, and after the first stage we've got the second stage, which is about the terminal velocity. And so here's our opinion part and the statistics part. So the first circle is about our first stage. So that's when we cannot get a constant and a stable phenomenon. But after the first stage, when the washer contacts with the rod with 2 points, then we got the terminal velocity and it got all the way to 3 seconds. So the first stage on the rods, following shows in red. So the slope is like this, and the slope doesn't change, so it's a terminal velocity. So the yellow arrow shows that the second stage of the rods following is steady. The final motion is stable, so we get our terminal velocity. So here's our opinion, and according to the experiment we can find the final motion is stable, so the ring can reach terminal velocity. It happens in the second stage, and we have to study what will affect terminal velocity in our first stage, since we touch the 2 contact points and we've got the second stage. So here's the analysis in functions. So our m is the mass of the ring, and Fc is centripetal force, and R is inner circle radius. So since we got 7 different rings and 4 different rods, so we can do tangent compares. And what we found out is that if the mass of the ring is larger, then the time for it to finish the first stage will be faster, and it leads to a faster terminal velocity. And there's another external limit that if the ring is too small, then we cannot fit it into the rod. So it's another force of difference. So the f of f and omega square. So we got a better theta angle. So the omega square will be larger, so the force will be quicker. So we can get a better terminal velocity. And here's the analysis in functions number 2, and here's about the torque. So the torque plunge is a normal force torque by gravity, and the torque F is the torque of the function of the friction. So what we can see is that in this model, so if we consider that the rod is over there in the green line, so we can get minus mg and mg. So what the force about the rod gives the ring is F over there. So we can get a force and torque be given to the ring as torque F plus torque of G equals deviation L over T. So here we can clearly get the deviation, and because of torque equals time varying rate of angular momentum. So here's another model force breakdown. So we have the angular momentum and the contact point. And since we got the 2 contact points, we can travel it to the second stage. So about the time we spent in the first stage, we can affect the terminal velocity by causing different conditions in the second stage. So the ring's movement direction is contact point with the rod. And here's our conclusion. The motion is stable in terminal velocity in the second stage of our definition. And while the inner radius of the washer increases compared to the same rod, the time in the first stage decreases and leads to larger terminal velocity in the second stage. So that's what I just mentioned. And when the washer contacts with the rod in 2 points, torque and normal forces get balanced and lead to terminal velocity. And the last point is force from the hand does not affect terminal velocity of the hedge. Here's the end of our presentation, and thank you very much.
Okay, thank you, reporter. So from your presentation, I saw that you had experimentation comparing the initial forces. Did you have any other experimentation that compares any other variables except for the initial force, such as the radius or the mass?
Radius, I believe you're talking about this. This one.
So did you visualize this using a graph or?
Yeah. So the graph we would put on is the best example. So we got different relations between
So this one has the same rod and ring. Do you have anything that compares the different rings, like for the graphs?
For this graph,
so you don't?
Yeah.
Okay. Do you have any video footage tracking from the top to track the rotational motion?
Yeah, but this too is only from the side, right? Yeah.
So did you track the rotation of the washer or not?
Yeah.
Yes.
Like we travel it by each video squares.
Okay, so is this the video that you took?
Yeah.
Then it's from the side, so it seems like the camera's perspective would be skewed. Is that correct?
I don't think so, because like what we take is from top to the bottom, and since we cannot shoot it from top.
But for the angular velocity, for the rotation of the washer, would that be correct or not?
So angular velocity actually depends on, like in our experiment, it depends on the mass and the radius.
Did you test the threaded rods in this case?
Sorry?
Did you test threaded rods? Threaded rods with thread? No?
No.
Okay. For the graphs, do you have error bars or anything that shows the error in your data?
So this is actually a 2 experiments, so we can just
So you do not, okay. How many contact points do you assume? 1 to 2, is that correct?
Yeah, from the first stage is 1, second is 2.
How do you think the mass would impact the phenomenon? Would it or would it not?
It will.
Did you test this?
Yeah.
Where?
Like in our conclusion.
The conclusion isn't that tough.
送来了干嘛？什么送来了？有人要送来了，送他不要急，公司很好。
Dear judges and competitors, my name is Thomas and I'll be presenting the opponent presentation for Ring on the Rock. So this is a problem statement, and the main focus that the opponent, the recorder should have investigated is how does the washer transition from the sliding motion to a spinning motion, and what parameters affect the translational and rotational velocity of the washer. So the opponent solved the problem by investigating the phenomenon and analyzing the forces that were acting on the washer, and then they incorporated some external equations that were pre-established, but did not create their own theory for the washer's motion. For the experimentation, the only variable that I saw was experimented was the initial force. No other forces, including the mass of the washer, the radius of the washer, was experimented or shown as in the presentation with their graphs. So some pros of their report. Their pros is that they show their experimentation setup in their presentation. They explain what possible errors could have occurred, and explain what parameters might affect the terminal velocity, and they represent their data using the graphs. However, their presentations cons are that they do not have experiments that verify their theory, or do they have an actual theory that investigates the motion of the washer. They do not explain the effects of the precession of the washer. They don't consider both threaded and smooth rods, only consider smooth rods, and the setup has the possibility of making the experiment inaccurate by not being stabilized at the top. In addition, there is no explanation or derivation of a theory from the phenomenon, and it is, their explanation is inaccurate on the washer's motion. Thus, their experiment, thus their task is partly fulfilled. So during the discussion, we will discuss the connection between the angular and translational velocities and how they relate to one another. And we will also talk about some other parameters that affect the washer's terminal velocity instead of just discussing the radius of the washer or the initial force, including the contact points at different radii and the use of smooth and threaded rods or the mass of the washer. In addition, we'll also talk about their questionable experimental methods, including their setup accuracy, such as their setup not stabilizing the rod from the top, which would cause the rod to rotate go from side to side, which would affect the washer's motion, and the camera distortion, where the camera was filming from the side, and the process of the washer's transition from the free fall to terminal velocity. And we can move. So first, the reporter. In your experimentation, did you have anything that stabilizes the rod at the top? Could you show your experimental setup?
Like we use our, because if we put the force on rings, it would actually rotate. So we actually just use our hands to stabilize the rod. Have to make it not move.
So do you think that was stable enough to not affect the washer's motion, or do you think the rod's motion would have also affected the motion of the washer? Because I think that the rod moving would have also affected the washer's motion in angular or translational velocities.
Yeah, I think even we use the hands to stabilize it, and it will actually affect one.
So are you admitting that your experimental setup is flawed?
It's wrong. Yeah, a little wrong, but I think we did the best in the show.
Okay. Can you go on to your graphs?
Okay.
So, are these the only two experiments that you conducted with varying, with variables that are different, such as the initial speed?
Again, these are not the only, but I think this is the best way.
Then can you show the graph with different mass or different radius?
Oh, we didn't put it on the board.
Okay, so do you have the data at least? Didn't you have the table?
Oh, we didn't put it on, so it's only
before the slide before this one.
This
one. So this one. So from this, did you experiment all of these washers and get their terminal velocity accordingly?
Yeah.
Okay. Then from this, it seems like their mass changes, but their radius and outer radius also changes. Yeah. Did you try experimenting by changing only the mass, or only the inner radius, or only the outer radius, and see how that affects the experiments and their terminal velocities?
That's actually a technical file because we can't actually conclude that by that.
So you had to change all three of these variables.
Yeah.
So you cannot conclude that which variable makes a difference in your terminal velocity.
Like actually in the material ratio, so I think.
So you do not know.
Yeah.
Okay. And for this, okay. And your contact points, you said you went from one contact point to two contact points. Is that correct?
Yes.
Okay. And for this, for your experimentation, did you take the rotational motion on the top view? Do you know what your terminal rotational velocity is?
I know. I take it from top view, but I didn't put it on top.
So you did not present any of your findings on your presentation. You did not present any of this. You did not present any of your terminal rotational velocities. All you presented was your two graphs that had the translational velocities. Is that correct?
I think terminal velocity can be shown in this curve by slope.
So you only showed ring F and not any of the other rings that you presented here?
Ring F and rubber, yeah.
So this is all your data that you present on this presentation?
Yes.
Is that correct?
Yes.
Okay. Did you consider the experimentation of smooth and threaded rods? So it seems like you only tested the smooth rods. Is that correct?
Yeah, we don't test the smooth rods, but we thought of threaded rods, but yeah.
How do you think using threaded rods would affect the experiment? Would it change the terminal velocity?
I think it's mainly about the friction, so I think it will slow down in the first stage.
Sorry,
so I think
increase the what? What did you say? Sorry.
Increase in friction.
Okay, how would it increase the friction?
So I think in the smooth part, the contact points won't be affected by the threaded parts. So I think in the threaded rods, time in the first stage of our experiment will decrease, so maybe it leads to lower velocity.
Okay. And your experimental setup, your camera. Let's look at your experimental setup again. So this as a side view, although you didn't present your angular velocity data for some reason, this would result in an inaccurate angular velocity because the camera's viewpoint is going like this, which would cause the back of the washer to appear smaller than it actually is compared to the front of the washer. Do you think that is correct?
Yeah, what would command?
So would that result in a false angular velocity at this point on the back of the washer or not?
So,
do you think angular velocity is still accurate in this case or not?
yeah, I think it will.
So is it accurate or not?
Is it not that accurate?
So your experimental setup is again flawed.
Yeah.
Okay. How would your washer transition from the from the falling to the spinning?
From falling to spin.
Yeah.
I think it's by contact point, so if we release it by our hand, it starts spinning.
So as soon as you release it, is
As soon as it's contact to the rod with the first point.
Sorry.
So we put the force on the rod, so that contacts with the rod. So the ring, so while the ring contacts with the rod in first point, and I'm sure that it will start spinning. And like when the angle gets bigger, then it will turn in the second stage, like spinning in the rocket.
So it would spin and start with 2 contact points or not?
It will start the first contact point, and as the angle gets larger, it will start the second stage.
Okay, could you show your video? Was this a video?
Yeah, but
could you show this one again? It seems like there's 2 contact points to me, but sure, okay. And as you can see, again, the experimental setup is flawed, that your rod keeps rotating at the top. Okay, for the mass, I want to ask you, would you think the mass would affect the phenomenon or not? The mass of the washer, and how would it affect it?
so I think from the functions we gave in the end, so I think when the mass increases, then you will short the time in the first stage. So when the time of the first stage shortens or increases the velocity.
Okay, and how would so the terminal velocity would increase?
Yeah.
Okay, I would think that terminal velocity would not increase, would stay the same though, sure. What? Sorry. So you didn't track the angular velocity at all. I think you should have tracked the angular velocity in this case to see how the washer rotates and how, if angular velocity relates to the translational velocity, do you think those two will relate to each other or not?
Yeah, I think it will.
How do you think they will relate?
You mean the angular velocity?
Yes, and
so,
the translation.
So in the functions we give the angular velocity, the square of the angular velocity and the mass. So the fact in the first part, so in a increases terminal velocity.
Okay. Can we go to the next slide? Yeah. Sorry, keep going. Okay. For this one, did you tell us which rod you're testing in this case?
It's again the third line. It's the same as this one.
Okay. Okay, now let's go back to our discussion on the smooth versus threaded rods.
Okay.
So you said the threaded rods would affect it how again?
Yeah.
How would it affect?
So you mean the third rod's effective motion?
Yes.
So I think what I just said is for the friction.
So it would increase the friction. So how would that affect the terminal velocity, which is what we're trying to investigate in this?
So I think the friction, like the friction gauge almost like increases, so the force will increase, so terminal velocity will lower.
So the friction would increase. Can you explain how the friction specifically increases in the use of a threaded rod?
Like the contact time between the ring and the rod. So like
you mean the surface?
Yeah, the surface part. So it touches certain part.
Are you claiming that the surface area would increase the friction, or
because of the third rod?
So you're saying that the surface area matters for the friction?
Surface area, because there are contact in points.
The contact area. You're saying the contact area matters for friction?
Yeah.
Okay, I would say the contact area does not matter for friction, but and also even for a threaded rod. So let's look at this. Even for a threaded rod, even if it looks like this, if the space between the threads are not big enough for the washer to fall in between, if the washer is thick enough, then I personally think that there will only still be one contact point, then one contact point on this side, resulting in 2 contact points. Do you think that is true, or do you think that this will result in an entire surface of contact?
Like the 2 contact points?
Yeah.
So like the 2 contact points always change as it spins, right?
Yes.
So that's the reason why I think
so it still maintains the 2 contact points that you said?
I also say this too.
Oh, on the threaded rod. on threaded rods?
On the third, yeah, it's always two.
So if it's 2 contact points, can we view the threaded rods as just having a slightly larger radius than it is? So the thread would be included in the radius of the rod. Do you think that's justifiable?
But can you assure that the rocker will touch the like lower point?
So if this length, let's say this is A, if this A is smaller than the thickness of the washer, this is smaller, then do you think this would be justifiable to say that this radius is greater than?
So if the contact point is always on the larger part, so
yes.
So it doesn't matter. So we can view.
So we can view it as this as the radius.
But can you assure that the ring is like touching this point and this point?
Yeah. So I'm saying that the radius, the thickness of the washer is smaller than this. Is greater than this.
Yeah.
Sorry, this is greater again. This is greater. So if the washer comes into contact here, the washer was something like this.
Yeah.
So there will only be one contact point. Do you think that makes sense?
One contact point.
Yes.
You would believe I didn't actually get it.
Okay. The thickness of the washer is thick enough so that the washer will not fall in between of these points.
Okay. So if I show that in the next one, then it increases in low.
So you still think
rotates in low.
you still think this. So I think that it won't have one contact point, it will be the same as a smooth rod, and you can assume that the radius is slightly bigger. So you can include the threads in the radius. But do you think that it would differ because of friction, is that correct?
I think in the division part, then I think it wouldn't really work because like you can assure that in every moment it's a little larger.
Okay. Let's talk about the rotational velocity. So do you think, so rotational velocity in this case, so for the threaded rods, do you think rotational velocity would change as well?
Yeah.
Okay, again, I think that rotational velocity would stay the same as well. For the smooth rods, you said you had experiments, but how did the smooth rods, in the smooth rods, how did the radius or the mass affect the rotational velocity, angular velocity?
Angular velocity.
Yes.
So I think the mass increases in the angular velocity, the delta of the angular velocity will increase over time.
Okay, let's say the mass does not
Time is up.
affect the angular velocity, sure. Oh, okay. So we had a discussion with the reporter. As you can see, the reporter's data is very minimal. They have minimal experiments, and their experimental setup is flawed. So in our discussion, we tried to discuss the setup, how their radius, how their rod isn't stabilized, which would affect their final terminal velocities. They did not use threaded rods, and this is, again, supporting their minimal data collection. And their camera viewpoints result in a false angular velocity, and their experimental setup is again flawed. Experimental data, their graph is, they only have one graph, one or two, and then they didn't test enough variables, and they should test even more variables to present more findings. Their parameters, their mass, I think that the mass does not increase the terminal velocity. The threaded rods, they say that it would increase the friction, and the terminal velocity would therefore decrease. The surface area, although they say it would matter, I personally think that the surface area does not account for friction.
Okay, thank you for the report, and I'm the reviewer. And first question I want to ask is, in your experiment, you use 3 kinds of different variables in just one experiment. Why that just like the opponent said, and which one is the main process that affects your experimental result? Is the mass or the inner circle, in the radius, or the outer radius?
I think it's because the mass and the inner radius.
And how about you?
I would say it's the inner radius of the washer.
Okay. Now let's talk about the next question. And did you consider about the slide of the washer, like beside the rotating, it will have a slide down?
So I think when it starts spinning, I don't have to consider that.
How about you?
Sorry, can you repeat the question?
The slide of the washer, like slide down, just fall down. Did you consider about that?
Yes, so it will slide down at the beginning and then start to rotate after rotating.
Okay, the third question is about, did you consider about linear velocity?
So I think the terminal velocity is linear, so
How about angular velocity?
angular velocity,
Okay, and how about you? You think have to consider about linear velocity?
I think that angular velocity is very crucial at this point, since the washer is both rotating and translation, and there's also translation function at the same time.
Yeah, I understand. And another question is about the opponent say the rod will shake, and we also saw that in your observation video. And Did you think that will affect the experimental result if the rod was shaking?
I think that will.
And how about you?
The rod shaking would affect the terminal
Yes.
velocity. Of course it would affect the terminal velocity.
Do you think the rod shaking will that the washer more faster to come to the terminal velocity or slower? And how?
So effectively, what the washer shaking is doing is it's effectively increasing the radius of the rod. You know what I mean?
Yeah.
So by increasing the radius of the rod, I think that the washer's angular velocity would decrease in that case.
Okay, I understand. And the next question is, do you consider about using a tracker on the top of the rod?
I use a tracker from the side view.
Okay. Do you think it's from the side view or on the top?
As I said, the camera is from a viewed perspective. I think that they should have two different perspectives from the side and the top to track the angular and
The
translational.
next question is, do you think about using the parameters like the different materials of the rod will be better if you have another experiment?
Yeah.
How about you? Different
Yes.
material. And it will,
Wait, sorry, the problem statement says the metal rod, isn't it?
yes, like different metal.
Oh, sure, no, different metals, sure.
Okay,
It would change the friction coefficient.
Okay, and what's the way to control your initial force? Like you using your hands and you say you control the initial force. And have there a better way to control your initial force?
I think using clip or something else like that.
And have you something to can improve the?
I think, to improve on our presentation.
Yes.
Thumbs up.
Look like all this. Oh, yeah.
Okay, thank you for the report and the opponent. Here is I'm the reviewer of this question, and here's the problem statement. We are main focused on the terminal velocity, the angular velocity, and the slide down of the washer. And here's the summary of the report and the pros and cons. And the phenomenon that they have not explained, and the theory they use is 1 and 2 contact points, and the angular velocity, the torque, and he has did some analysis in functions, and he has did his experiment in 7 kinds of rings and 4 kinds of rod, even they just have different kinds of variables in just one experiment, and only shows changing initial velocity. And the process that he gave many potential parameters like he did, and explained first the diagram of the rig and experimental setup, and he showed on his report, and he has no observation video and no phenomenon explanation, and does not quantify the initial speed. And page 9, he didn't, there's miscalculated the rotation radius and did not show the experimental data and the conclusion, and for time management didn't consider about the precision. And next page, we're going to talk about the opponent. He has a clear and consists on short questions like he just did, and point out the shape of the rod that we have seen too. The point of the followed experimental method like the camera have to be on the top and have an understanding of the report and bad time management, and did not give ways to improve the state setup by the reporter, and did not clarity the terms like this, and didn't talk about the terminal velocity, the friction about the rod. And here's the discussion of their first question about the rod is stable, and this we have seen this too. The rod may be, the reporter says the rod may be stable and will affect the motion of the washer, and the opponent says that they did our best to control it, and we think its unstable rod will affect the consequences, like the terminal velocity, and we have asked initial question, and they discussed about the smooth or the threaded rod, and the reporter says, well, it has impact, and the friction will be different, so so the opponent says the friction will be different, so will lead to the lower velocity for the straight rods, also can be seen as the larger radius of the rod, and we think the smooth rod will cause increase the linear velocity, so that has to be considered. So the next question is about why will increasing in the mass effect, and the reporter says that the terminal velocity would be the same. So the opponent says that the less increase the terminal velocity will maybe increase, and we think if the mass increase, the first stage will be shorter, like the reporter says the first stage will be shorter, however terminal velocity will increase. And here's the missed point of the reporter and the opponent. They did not seriously the parameters is most important. Like they just have the different rod and different rings, and there's 3 kinds of parameters in just one experiment, and they have not definition of the terminal velocity, the linear velocity, and the angular velocity. If even they say that is important, and the shaking rod, the opponents say will increase the infection radius. And here's some point they didn't point out, like did not explain how the friction will affect the motion. For example, the first diagram has the boundary conditions of different stages. Okay, here's my presentation. Thank you.
Okay, so I have to thank the opponent and the reviewer for making my report, and here's my concluding remarks. And I have to thank for the comments of the opponent and reviewers, and we've discussed different strings under certain circumstances, but other situations should be considered, and our parameters and our data and our experimental setup are too raw and not accurate enough. We have to make more comparisons about our experimental data and how we make our theory. Here's my remarks. And thank you.
It's time for jury to ask questions.
So my understanding is that you didn't study the rotational parts of motion. You just study the terminal velocity, which is the velocity of, say, the center of mass. Is that correct?
Yes.
Question to all 3 teams. How do you think the mass will affect the terminal velocity, and why?
Okay, so I think the mass will increase the angular velocity when in our terminal setup in the first stage. So it will lead to better terminal velocity, like larger terminal velocity in the second stage will lead to the energy.
So I think that the mass would actually not affect the terminal velocity, although they tested different parameters on different rings that also changed the radius of the washer and the radius of the inner and outer radius of the washer, which is what affects the terminal velocity of the washer, not the mass.
But why would it not?
So in this case, if you keep the shape of the washer the same, but basically decrease the washer's decrease or increase the washer's mass. What it effectively does is, although it increases the gravity that pulls it down, it would also increase the friction that pulls it up, which equilibrates both of the forces and causes the terminal velocity to stay the same, rotational or angular.
I think if the mass increase and if the angular velocity hand gap, the ring didn't change, so the linear velocity won't change, so terminal velocity won't change too.
So, I have another question. Do you want to? I have a question that so you were talking about other parameters today, and what would you do if you want to for sure reduce the terminal velocity? What kind of parameter can you tune? Can you just name one and sort of?
So by making the inner radius of the washer and the the radius of the rod very close to each other, it will have a very small translation per rotation when it's going down. So that would increase the time it takes to get down, which would decrease the terminal velocity as well.
Yeah, so I think I can decrease the inner radius of the ring and also really increase the radius of the rod and also change the rod to like a 34 to increase its friction.
Okay, and I want to say is that you have to change the linear velocity, and so you have to have a bigger friction. So you have to use different kinds of materials that have different kinds of friction, the coefficient of the friction, and to change the linear velocity, you have to decrease the radius. But about the angular velocity, you have to increase the radius, and the friction is still have to change because to increase.
Can I see the reviewer's report again?
Oh yes.
Just to make sure that.
Yes.
Sorry about that, but it just it's done.
This one is.
It's upside. Yes. We have to switch the opponent and reporter.
And so is this one.
No, just that one. The mass. All right. But I thought you just answered the question.
Sorry, I said the terminal velocity would stay the same, increasing the mass. The reporters, the reviewers.
No, I'm asking the reviewer. I thought you say, when you answer the question, you say it will not change. But you say you will increase here.
No, no.
Huh? I thought you said it will not change, right? You were answering the.
Doesn't affect the terminal velocity. That's what I heard.
Yes.
And he gave
the substitution switch.
No, the button. Your own opinion. The reviewer's opinion. I just want to make sure if I'm hearing correct.
Well, when I asked you a question, you said it will not fit me.
Right. That's what I heard.
Sorry about that. It just.
Yeah, we're asking the reviewer.
Yeah.
And she.
Yes, I understand, and sorry about it. I just made some mistake, just like typing wrong.
Oh, okay.
Or change.
Okay, fine.
I think time's up, and it's for reporters, jury should give score now.
He's not done yet.
Not done? 5, 4, 5, 6, 6.不到。 Now for the opponent. 8, 8, 7, 9, 7. For the reviewers.
First 9.
7, 7, 6, 7, 6.
No, no, the name from right to left.
Yeah.
Let's have the opponent to challenge, to choose a question to challenge the reporter.
So I'd like to challenge question number 14. We reject number 14, ball and language. I'd like to challenge question number 7. We accept number 7, please sign it back.
OK 了吧？然后反正我这边这边一样是登记那个你们对，我说我纸本这边，假如说等下进去。Sorry for technical issue.
Oh, it's alright.
Okay.
Oh, never mind. Good morning, everyone. Today I'll be presenting the three-sided die. My name is Abshok and I'm from Nomads. The problem statement reads, to land a coin on its side is often associated with the idea of a rare occurrence. What should be the physical and geometrical characteristics of a cylindrical die, such that it has the same probability to land on its side and one of its faces? The main focus we will be discussing is 1. How should the cylindrical die be rolled to ensure randomness? 2. What relevant parameters affect the landing of the cylindrical die? And 3. How can we use these parameters to find the physical and geometric characteristics of the three-sided die? So we'll begin with the phenomena investigation, where we define a cylinder and talk about the chaotic system. Then we'll move on to a theoretical model with assumptions, edge-induced faults, energy loss, and the best escape probabilities. Then we'll talk about experimentation and discussion with our setups, results, and some ideal characteristics. So here is what we define as a cylindrical die. So we define this die as a cylinder with a radius r and a height h. And we also define P of edge as a probability of landing on its edge. So here is a quick test. So here is a video that shows the depletion of energy from inelastic collisions of the die on the surface. I say it's inelastic because it loses energy in these collisions. Note how we dropped in from the very similar initial conditions, both facing heads up, while this one landed on its head, this one landed on the side. This shows that the system is chaotic, because when the die is rolled from high enough, it has a large enough potential energy, which shows that it's a chaotic system, meaning that it is sensitive to initial conditions as shown in the video. This means that the rolling methods will not affect the landing of the dice. So So now we begin to derive our theoretical model. First, we'll make 4 assumptions. The first one being that the size of the die does not affect the probability of it landing on its edge. The second assumption is that the dice is rigid, which means it cannot deform. The third one is that the surface is rigid, uniform, and perfectly flat. And the fourth one is that dice does not lose energy while it is falling. So here we begin with our first geometrical definitions. So we have eta is equal to the ratio between the height of the dice and the radius. And we have L to be equal to this length, so half of the hypotenuse of the triangle. And we also have beta, which is the enclosed angle between these two. So we have our fall definitions. Over here, we have 2 diagrams of what we call edge-induced falls and head-induced falls. What they mean is if you drop the dice at rest from one of this position, if it is in an edge-induced fall position, it will be more likely to fall upon its edge. And if you drop it from that position and it will drop on its head, then we call it a head-induced fall. And we define those probabilities with P of E and P of H. So here's our bounce model contact point. So let a point on the circumscribing sphere of the die represent how the floor will contact the die. So you have a circumscribing sphere and all tangent lines to that sphere can be moved inwards such that they contact the die. And that will represent all the possible ways the floor will contact the die. So we can base our contact probabilities on this. So in the shaded green area, that shows the probability that it lands on the top or the bottom area. And the probability of E shows the probability of it landing on the middle area, which is an edge-induced fall. So we also use sterradians to quantify this. So it measures the area on the surface of the sphere. What it does is quantifies planar angles and is analogous to radians, except instead of measuring from 0 to 2 pi, we measure from 0 to 4 pi. So here's a visualization. Here, we also use spherical coordinates, and here are our definitions. We define R to be this vector, phi to be the angle between the x and y axis, and theta to be the angle between the z axis and the xy plane. So first we found the edge solid angle. So we had a surface integral over ds, and this is a little bit complicated, so continue. We derived this after our surface integral to be edge solid integral will be 4 pi sine of theta. So our bounce model contact probability shows that the probability of an edge-induced fall will be the probability of the middle area. If you remember, that middle area was the one that was shaded in red in our diagram, divided by the total max solid angle. So that will be 4 pi sine of theta divided by 4 pi, which will give sine of theta. And thus, since the probabilities of edge and head add to 1, 1 minus probability of edge will give the probability of a head-induced fall to be 1 minus sine of theta. Only change the slide if I ask you to. Thank you. Move back. What do we do next? So here is our bounce model that shows the energy loss. So let gamma equal the ratio of energies before and after each bounce. So since it loses energy constantly, you can derive the coin energy after n bounces to be energy of n will be equal to E naught times gamma to the n, where n is the number of bounces. Here is a visualization of that model. On a given bounce, the coin has a kinetic energy epsilon we define, and well m about center of mass. We'll define that well later. So when the coin escapes, it will reach a state after which the bounce, where it's diagonal, is perpendicular to the floor. You will notice when it's perpendicular that this is neither a head-induced fall nor an edge-induced fall. A little change will change it to either side. So basically, if a coin has enough energy to reach this state, then it can transition from an edge-induced fall to a head-induced fall. And we call that energy required to be the well. So here, please go back. So here is a demonstration of a coin that fails to escape because it cannot reach the well to reach the situation where its diagonal is perpendicular to the floor. So here's a graph of well versus angle to surface to visualize it. Now we define our escape probabilities. We define our escape probabilities, f of epsilon m, as the escape probabilities. What are its probabilities? So if the energy is less than the well potential energy, then it means it cannot escape from an edge-induced or a head-induced. Therefore, the probability of escape is 0. And the same applies for when the probability of when its potential energy is greater than the well. And this is, again, our definitions for edge-inducive and head-inducive walls, respectively. Next. So we can have an integral of the escape probabilities shown over here. Again, it's a little tedious, so we'll move on. And now we can calculate the escape probability of an edge-inducive wall through an integral over the edge of the solid angle. Next. Here is the derivation for f of e. Move on. So you can see that will be 1. Keep going. So now that you have f of e, f of h will be very similar. So now we have the probability of it landing edge on its ith bounce will be the probability of the coin landing on the edge on the ith bounce as we defined. So the probability of it landing on its edge will be the total sum of the probability of it landing on its edge on the kth height. And we have the probability of the coin escaping on the ith bounce to be very similar because we have to multiply all the times it does not escape. So this is the time it escapes on the 0 to I-1 bounce. Next. And this comes to rest on the ith bounce. So basically what we can do is we can sum up all of the possible escapes to find our bounce model over here. So now we move on to our experimentation and discussion to verify our theory. So first we determined the coefficient of restitution by calculating the initial and final heights for 5 heights and 28 tails. Here we have our graph. And note that the coefficient of restitution will be the square of gamma, which we'll show later. So gamma will be the final height over the initial height, which will be the square of the coefficient of restitution. This is because rather than the coefficient of restitution being defined as a ratio of heights, it's actually the ratio of velocities. And from our experiment, we determined that the coefficient of restitution between the dice and the floor we were testing on was gamma is approximately 0.6437. And here's our experimental apparatus. We have multiple die. For example, over here, our 5 cm tall die is shown over here. This is the die has a radius of 1.5 cm and a height of 5 cm. So for our experiment, we have 3D printed uniform dice made out of PLA, which is basically the robotics things. And then we have a uniform floor, and we repeatedly roll die on the floor from at least a meter high. The reason we want to do it from a higher standpoint is because it makes it more random. Because if we just drop the die from here, it might not bounce as much and contribute as much to the chaos. And we kept track of the faces and sides. So for example, after dropping, if it lands on heads, we write heads. If it lands on sides, we write sides. Next. So here's our graph between probability of it landing on one of its edges versus a top, which, as I mentioned earlier, is the ratio of the height to the diameter. So here's our theoretical model, which we graphed in MATLAB over here. And in blue, you can see our experimental results with error bars. We have a horizontal line over here that shows the intersection of 0.3333333, well, 1 over 3, which is, because it is a 3-sided die, we want to find probability 1/3 of landing on its side or on its head. That intersection with a theoretical value so that we can find the optimal setup or the optimal ratio between the radius and h. Over here you can see our trial numbers. We have over 2,000 trials, so that shows the validity of our trials. If it does not show our dedication to this project as well. So the graph is the same for large enough epsilon naught. So the characteristics for a cylindrical die with gamma equals 0.647 will be A tap, which is the ratio between the as height and blah blah, to be 0.5747 for 1/3 of the size. The graph is created using simulations with other variables of gamma. So here's our conclusion. Our summary is that the 3-sided die is a chaotic system. This means that if you drop it from high enough potential energy, it will be sensitive to initial conditions. That also means that the rolling method will not be a factor because no matter how you drop it, it's going to be random. The relevant parameters in our experiment will be A top, which is the ratio of the height to the diameter, and G, gamma, which is the square of the coefficient of restitution. And ideal characteristics would be an ideal value of A top, which is dependent on gamma, and on the intersection of this graph. And here are our references, and thank you.
Thank you. Can you go please go to page 22? Go to page 22, please. what is M here?
Sorry?
Yes, what's the M?
It means the well energy. So it's
No,
the
well energy. Okay.
Yeah.
Can you give some because the problem statement asks us, can you give some physical characteristics that will influence the initial condition? Just give me a few.
So influence, we already mentioned earlier
Yes.
that the
What are the
initial
physical
conditions,
characteristics?
they don't matter because it's random.
Okay, so no physical
So you
characteristics
can like
yes or no?
angle,
No physical
velocity,
characteristics
They don't matter.
Okay. When you use 3D printer, right? Yes,
yeah.
right. And you do realize that the top and the bottom of the 3D printing is different.
I do realize that we use
And
sandpaper.
And do you realize that the edges are not a cylinder and they are actually more like a polynomial?
I don't know what you're talking about.
And does a fair three-sided dice exist? So is it possible for me to create a three-sided dice that will have one to one probability to land on the side and the face and its faces?
Last time I checked, 1 divided by 3 was 1/3, so it should be 1/3, 1/3,
No, no.
1/3.
I mean, like, is it possible to create a fair three-sided dice that I can land on each face with the same
Isn't
probability?
this the entire point of this
Yes or no?
Yeah.
Okay. And what parameter is the most important? Because you said you need to have at least a meter of drop height. So do you think the drop height is important?
It ensures randomness.
Okay, but drop height is
But I think the most
physical
important
characteristics, right?
parameter
Is drop height
8,055
physical
as-
characteristic?
Yeah.
Okay, but you said physical characteristics do not matter to your
No,
results, right?
I thought you were talking about like,
I said
well, if
physical
it's
characteristics.
random enough, it doesn't matter the other
Okay,
physical
thank you.
characteristics.
Thank you.
If anything, it just makes it even more random.
So I'm Joey from team 9120, and I'll be the opponent for this question. Okay, so problem statement. Today I'm going on site in the office. I'll show you. Okay, what should be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability then it's sighted when its faces? So here, the problem statement clearly asks us to investigate the physical characteristics and the geometrical characteristics that should form a three-sided dice. Okay, so summary of the report. It has sufficient theory, which we will come back to, and it has many charts and graphs, and the experimental data results fits the theory very well. And the cons are that it lacks the explanation of the theory, and it changed the site too many times, and lacks connection between the theory and data, which I will explain, and it lacks enough data. I only see a few variables, and I believe that their experimental times are insufficient. And they lack physical explanation of this phenomenon. And since we're in the physics debate fight, I think that is very important. Okay. So point 2D, let's discuss. First, the phenomenon explanation. So the physical characteristics, they believe that the energy will decrease, and they can, and we'll be discussing whether we can control some initial condition, and whether what initial condition matters to the results and what does not. And as I mentioned, bouncing, because they have this restitution coefficient. So does bouncing actually affect it? And the geometric characteristics, which they did explain, however, they did not give clear derivation. For example, what the exact value is for eta at their theoretical site. And does a fair three-sided dice exist is what we will be focusing on mainly, because if a three-sided dice does not exist, then we have to investigate what's the reason. If it does, then we have to state what the physical and geometrical characteristic is. Okay, so theory, they use center of mass and for the geometrical part, and they use solid angle edge, solid angle. So they use whether the three-sided dice will face to the edge or to the face, and they also consider energy loss, bounce, and escape probabilities. And their experiment, although they stated that everything is random in their experiment, however, in their experiment setup, they use similar ways to drop the dice. So we'll be discussing about that, and also how they throw the dice. Is it really random, or is it not? So also, and they did not realize that the 3D printer, what the 3D printer prints out is actually not a cylindrical dice, but it has sides on its face. And for the parameters, they did not give enough parameters what will affect this experiment. And every experiment has to have enough parameters to support, and they have to fit their theory with it. And so we'll be discussing, for example, the proportion of the thickness and height, and what, for example, the initial velocity, or the initial drop height, or the initial potential energy is. Yes. Okay. So let's move on to our discussion. Okay. So let's start with our problem statement. So you do realize that the problem statement asks us for the physical and geometrical characteristics, right?
Yeah.
Let me ask you again. So would you give some?
As I mentioned earlier in our assumptions, please go to the assumption side.
Yes. Just tell me, so let me make this question easier. So
I don't need you to make it easier.
Okay.
Here we have our assumption side. First, obviously, we wrote here very clearly in very large font that the dice has to be rigid, which means it cannot deform. You don't want to be throwing Play-Doh die.
Okay. And I agree with, because since you use 3D printed, it could be assumed as rigid. Yes. Please go ahead.
And what was your other question?
Yes. So because it asks us what the physical and geometrical characteristics are.
Please go to the last, one of the last experiments.
Yes. So, in my opinion, some physical characteristics will be the initial, for example, linear velocity, angular velocity, or the potential energy, or the drop height, or the force exerted on it? Can you agree on that, or can you give some?
I respectfully disagree because I only think the initial drop height and those things help contribute to the randomness.
So only initial drop height?
No, only as long as it is random, its physical conditions will not matter. To demonstrate this, I have a coin.
Yes.
I hold it every single time like this. Let's drop it and see what it does.
Well, can you ensure that you are holding it at the same height? Okay.
Even if I throw it up like this, it's still random.
Okay, good. This is a cylindrical dice. It's its diameter and its height is square root of 3 to 1. Okay, so this is geometrically a three-sided dice. Okay, so it does not say us how we should throw our dice, right? Okay, so can I use this one? So if I put it here, tell me, does it always land on space, right? And I am controlling its initial state, right?
Yeah,
so
as I mentioned earlier, we dropped everything from a meter high, so as I mentioned earlier, when its potential energy is great enough, it will become a random system.
Okay, so yes, I get your point. You mean that the height will affect it, right? Yes.
It will affect the randomness, but not its like physical.
So okay, so let me sum this up. So for this dice to be random, you have to have enough drop height, and you have to have
enough energy.
Okay, enough energy, and you believe that is 1 meter, and that is enough.
Yeah, 1 meter is definitely.
Okay, so let me ask you this. So for example, if you believe everything is random, okay. Ooh, sorry. Okay. So if I use big dice, all right, I put this into very big dice.
Yeah,
okay?
Of course. Then its height isn't going to be as.
But it has great energy, right? It has the same energy as this one, right?
Did my dice look like Godzilla? It's like this small.
Your statement was that
I had 2.5 cm and 1.5 cm.
So do you agree that it's more like a drop, like for example, the energy that it has compared to its mass? Because
I get your point.
Yes.
So I understand what you're trying to say.
So you agree, right?
No, wait. Why don't you let me talk?
Yes.
Okay. So maybe you're measuring potential energy from the center of mass to the ground, which would be correct. In this case, I'll have to reiterate again that probably instead of defining the potential energy as the height from the center of mass to the ground, I should probably have potential energy minus the radius of the thing.
Okay, so you should consider potential energy and the radius of, or you mean the distance, or
no, potential energy should be a function of. You should determine potential energy from the bottom of the dice. That's not how you determine it, but if you do mgh minus r, that's what I'm. So.
But I thought you were using the center of mass. Right?
Yeah, but what I'm saying
is it the center of mass in the center of the cylindrical dice, or is your cylindrical dice not homogeneous in?
What I'm saying is, instead of measuring from this to determine the potential energy, in this case it would be better probably to do it like this.
And what's the M? And what's the M right here? Yes. Okay. So I have never heard such way to determine potential energy, but it's okay. Let's move on to the next question. So okay. So because since you're talking about probability, all right. So everything has to be random. So okay. So there are so many things we have to. There are so many physical characteristics, so many geometric characteristics. Although you said they don't matter. So let me give you an example. So I can put it on different drop height. I have infinite amount of different drop height, right? As long as it don't deform. Okay. So I can drop it like all the way up there, and I have what? Infinite different kinds of initial rotation velocity, right? To the 3 axes, I have so many different kinds of physical characteristics. Okay, so if I were, ideally, if I were to control every single infinite physical characteristics, including the floor, would it be the same results if I control every single characteristics? So I have the same drop height, I have the same degree, so it's not like it's tilted a little bit, it's all flat, or it's all the same.
Okay, so give me 30 seconds to explain myself. So I think this is
because you answer my question first.
Yeah, I'm answering your question, but you keep interrupting me, so I'd like to finish. So this is becoming like a 20th century theoretical physics debate where it's arguing if the universe is deterministic. But how the hell are you supposed to measure 0.0001 degrees of slant angle? This is becoming a discussion of how to make things random, not the physical and geometrical characteristics as you pointed out.
I want to discuss about physical and geometric characteristics, but you told me that they don't matter and only randomness matters. So I'm coming into your
entire slide saying the geometrical conditions is eta equals 0.5764.
So only geometrical characteristics, right? No physical characteristics. So you are not fulfilling what the problem statement is. So my suggestion is that we can consider physical characteristics. For example, you can do from the same drop height. If I use a machine and then have different initial velocity, initial rotation velocity. For example, 40 radians, 50 radians, 60 radians, and let's see what the results will be.
I bet there will still be 1/3, 1/3.
And did you do experiments to prove that?
It's a random system. If you spin it at
yes, so you're coming back to random, right?
3 omega versus 4 omega, it's still going to be random. So what you're saying doesn't matter. Because you can't control the machine to spin at 0.000000 infinite zeros 1.
Yeah, so what I'm telling here is I'm just giving you a suggestion. I know this experience is very hard, but
it's the easiest project in the entire thing.
Okay, that's something big to say. Okay, so ideally we can control this, but however, in the reality we couldn't control so many conditions. Do you agree?
Yeah, I agree. It's impossible to control.
Yes, it's impossible. So what I'm trying to ask is, if we cannot control this many conditions in reality, and how do you explain that all this condition, because for this infinite many of conditions, if each kind of initial condition leads to one result. So if I have a kind of initial condition, it will land on this face. On the side, if I have B, it will land on this face, and it goes on and on. Could you explain how these many kinds of initial conditions, all of them summed up to randomness, would be 1 to 1 to 1?
What?
Would be 1 ratio to 1 ratio to 1. Like the probability will be same.
That we had the surface integral as shown earlier. Are you talking about my theory right now?
Yes.
Okay. Would you want to use that for theory, please? Start with survey. Actually, the surface. Yeah. So actually, it's one more side. One more.
Okay.
So we basically have a concentric sphere surrounding the cylinder. So any tangent line to the sphere, moved inwards till it touches a point on the cylinder will give all the possible landings.
So let's move on to your experiment and your relationship with your theory. So this dice is not ideal, right? As you can see, it's actually actually has lines. I'm not sure about your dice. If you can show the dice, then maybe I'm wrong.
Okay, I'm showing it right now. Does this look like hexagons to you?
I can't find. Okay, so if this dice is not ideal, then why does your experimental result fit your theory?
It is ideal. This is a circle.
And can you show anything else what your possibility of getting to its top to its bottom?
Okay, wait. Eta slide. Probably next one. Okay, here. So the ratio between the height to the diameter should be 0.5747.
Yes, I know that, but where's the experimental results?
Backwards. Here are the blue is our experimental results.
And if it's free roll, right?
No, it's not.
Okay. Okay, so a summary of this discussion. The main problem of the report is that they neglected what the problem statement asked us to discuss about physical characteristics and geometrical characteristics, and they pushed this all on the randomness of this dice. So they believe that everything is random, but they still can't explain. For example, if everything was to be random, then why do I need enough energy, right? Then that I will be controlling something, right? If anything is random, I control it here, and it will always land on the side. So
So the thing is, this thing in reality is not random. The way we throw it, it's not. We could not be sure that it is random. So ideally, if it was random, then using the 1 to square root 3 geometrical characteristics, we can assume that this dice will have 1 to 1 to 1. However, in reality, 3-sided dice will not exist if we cannot control we cannot ensure that it is random.
Time is up.
Yes.
Okay, so I'll take the floor now, since we're both of you. Okay, so in the report's report, you mentioned the chaotic system. Can you give me your definition for chaotic system?
A chaotic system basically means small changes to initial conditions, even like 10 to the minus 10 changes will affect the final result drastically.
Then how will you define your chaotic system? Chaotic system.
Okay, chaotic system. So how we, if it was random, then every initial condition would change, and we cannot be sure that it will be the same every time.
You contradicted yourself. You are saying like, how would if you change the angle slightly?
Yes, but in reality we could not change it, right? Ideally, in reality we can.
Sorry, this is a time for review to ask questions.
So do you have the best cylinder that's for like after order 3 and experiments? Do you have the best exact ratio or that?
Yeah, it's the height to diameter will be 0.54.
So
57.
So besides this, do you have like a range, like it's accepted, like the possibility is accepted for the cylinder dice. Like for example, when we make dices, then we actually have a range. Like despite of the possibility of actually one fits, then you have a range that's accepted from like the size 0.5 or something.
I think I know what you're saying, but I don't think this is relevant to the problem statement. We're just trying to find us to design the optimum one, not to give a range of what will be statistically accepted in the casino.
Okay, so I didn't see like your statistics in your report.
We didn't. Yeah, we have error bars. If you go to a couple of sides over there, yeah, here are error bars.
Okay, so do you have like data about how you throw your dice?
We throw our dice at more than one.
I mean your data.
What?
Your data. Like about.
They might be at the very end. So you mean the data itself?
Yeah.
Unfortunately, we don't have our data, but we have our. I think it's unprofessional to show data without graphs, so we just showed our graphs.
Okay, then how do you assure like you throw your dice on the floor, right?
Because we're standing on the floor.
Yeah.
Or how do you assure when the dice drops and lands on the floor?
I think you do your experiment. Do you throw it on the floor or something else?
It's on the floor.
Yeah, then how do you assure the floor is flat? Then not depending on the trees.
That's in our assumptions. We assume that our floor is smooth. Yeah. You know those like devices that have a little bubble inside the liquid? Now when you put it on, it will show that if the bubble is in the middle, that means that the floor is smooth.
Okay, so in page 19.
It's page 9.
19.
Oh, 19.
Oh, so can you explain like the E from the?
Oh, you mean basic algebra 1? Sure. So basically you have the energy after n belts is the initial one multiplied by how many times the ratio of decrease the energy.
Okay, so here's my report on. Sorry.
What?
Okay, so here's my review on the three-side dice and working Tesla from High School. Okay, so here's a problem statement, and I will repeat it for the keywords of physical and geometrical characteristics and of the same possibility and probability. Okay, so here's my comments about the performance of the reporter. So I think the pros are that the radical model via literature used many functions to try to prove. They have great understanding of theories and thought a lot about how to balance the equivalence between the sides. And here's the cons of the reporter, and I think they failed to apparently explain the use of functions and mention a lot about the theories, but not exactly how they calculate. And they can do better in time management and fail to use a physical side to explain methods. And they're not mentioning of their experimental data, and mathematics should focus on data statistics instead of over-analyzing. And here's my comments of the performance of the opponents, and I think the pros are to ask some interesting questions and clear points about the problem of the reporter and good understanding of the report. And the cons are took too much what are relevant points of view and did not ask many important questions and lack of own opinions. And so here's their discussion topic, and I made like a summary. So the opponent, what's the physics characteristics of the dice and how would them affect? And does a fair three-sided dice exist? And the answer from the report is they do affect and did not explain how. And yes, and explain using etc. And here's our point of view. And we have considered models from 3D angles and 2D angles to ensure the expectation. And physical characteristic consists mass, size, and initial height of the dice. And yes, the ratio of the dice is important. Okay, so about the discussion of the reporter and the opponent, and I think despite of the theoretical drop, I think the most important for the dice, for the analyzing of the dice is to do it theoretic experiments and statistics of the data to get the exact range of the three-sided dice, and that's what I think is the most important. And here are the points that I think the reporter and the opponent missed. Like what size of the dice will not hold on to the expectation, and what materials will be the most ideal, and what's the range of probability and the ratio of the dice that is accepted. Again, I believe this is the end of my presentation. Thank you.
Okay, so here are my concluding remarks. First, I will say that the roughness on the edges of our die is minimal, and even if it exists, it will not impact the optimum ACA ratio. Because even if there are slight bumps on the side, which none exist, unlike the opponent's dice, it will still land on that side. Also, I'm very saddened to have the discussion completely about randomness. Instead of talking about our theory or our experiment, he just kept talking about why our experiment wasn't random, etc. But I would say again that it's impossible to control perfectly the inertial conditions in the real world, so that if enough potential energy is fulfilled, it is essentially random, and such a conversation is meaningless. Contrary to what the opponent said, throwing the die from similar positions from a large enough height will still ensure randomness. So if you throw a coin like this, it can land heads and tails on the same side. For what the reporter said, the reviewer said he wanted to find what materials affect the three-sided die. I think that as long as the material does not cause the die to deform, I think all materials will be equal. And what was I going to say? And I think the only important characteristics to ensure randomness is if you have a high enough potential energy, and the geometrical characteristics are shown by eta, and our experimental data verifies our data. Unfortunately, we did not have many fruitful conversations about that, but we're discussing randomness. So again, I would like to conclude that the three-sided die is basically a random apparatus, and such assertions to the contrary are fruitless. Thank you.
time for jury to ask questions.
I just need to see your page 35 again.
Yeah.
Very quick. What is that horizontal line?
This is the probability of landing on its edge, and this is 0.3 and 0.4.
What is
so
this
it will be,
horizontal line?
so that's 1/3. So we want to find the
That's
probability.
what you want.
Yeah, that's what I want to be 1/3.
And do you have a discrepancy between your model and the experiment? Did you calculate that?
Actually, for these two, you show there are some discrepancies. You see that the
Do
error
you have
bars
a
are
number
different.
for that?
No, unfortunately, I don't think
Okay, thank you.
Can I ask the reporter a question? I think you mentioned when you drop the dice, you roll it. You roll the dice.
because I'm not holding, I'm just like dong. So
That's not rolling, right? That's just release from stationary states. It's rest. Every time you hold it and then you just release it, right?
we have a lot of people performing our experiments. So some people like roll it, some people.
So that's one of the randomness there.
Yeah, it's a randomness.
You
Even though I
failed
believe that.
to mention that because I was thinking that when you say roll, of course you must impart some rotational motion. Otherwise, you will say just drop it,
I
right?
think it's impossible to not impart. Even if you try your best to hold it stationary and drop it, there's still going to be a little bit of
It was important that when you want to establish your result, that you state clearly under what conditions it's performed. I think that's what I'm driving at.
Okay, my apologies.
Okay, because if it's always the same, then assuming as you did that the air resistance doesn't matter, then the motion of the ice before it hit the floor is always the same.
But it's impossible to not have it rotate, so there's going to be.
No, I understand, but if you just every time holding it flat and then release it, neglecting air resistance, the motion is steady. Okay. So you must have some arbitrariness in your initial condition that will cause you the chaotic or randomness you want.
Sorry for not defining this as rigorously as I should.
Yeah, and I think that's what the opponent is driving at, right?
Yes. So what I mean is, if we can control ideally, then the results will always be the same. But however, in reality, when we do our experiment, what we can only do is, for example, drive it towards this condition. However, we cannot be sure that every time it will be the same condition. So I believe that, for example, as you said, if we drop it, every time there will be a slight rotation. However, if I drop it, then the probability that it lands on its faces and its side would not be fitted to the theory if I drop it as the best I could do the same.
Could I just make sure your eta is defined as h over r, right?
2r. So
2r,
h over
because
2r. So
r is 1/2. Okay. So the result should be interpreted. You say the eta should be 0.57 or something. That is above 1/2 to get the fair chance of landing on each side.
Yeah, a little more than.
Could you? Fair, yes.
1/3 and 1/10.
No, that's called fair. In the problem, that's called fair. F-A-I-R. 1/3, 1/3, 1/3. Yeah. But I'm asking that what's your intuition about it? That before you do the experiment, it is about 1/2.
I actually thought that it was by making it into a cylinder. I thought the eta would be. I thought the height would be a little greater. I was actually guessing around 0.7.
How about the reviewer? Do you have any intuition about this result?
Okay, so my experiment data is actually different, and our rate,
the eta is 0.5. It's above 1/2. It's over 1/2.
Yeah, but
You expect?
like our experiment are separated as like the height is 1 and the diameter of the cylinder is 2. So like we actually got
Okay, so
Sorry, it's all, no. Unless the,
It's
chair.
okay, just come true.
and,
Just into it.
okay,
no,
so
you should ask the chairperson.
answer. Do I have to answer?
And he answered.
Yeah, please.
Okay, so our theoretical would also be 0.547, but under the condition that it is not bouncy and it's like if it is at a static state. Yeah, so it already containing ground, and we only consider the center of mass and whether it is.
No, we were talking about the reporters
And that's not what we're
Yes.
So it's time for jury to show the score, and the score for the reporters, 7, 7, 7, 5, 7. The score for opponents, 6, 8, 6, 8, 5. The score for reviewers, 6, 7, 6, 7, 6.
I'm talking about what you think, what I think. That's my point.
So you agree it's not excessively low?
Eh?
Look at, 5 is not excessively low.
No, but compared to 8.
So it's 8, which is different.
We have 2, 8.
My suggestion to the opponent is that, like Professor said, you can go, you should try to pursue follow-up. If you don't get a satisfactory answer, then you should get more.
But you gave 8.
Yeah, because I think.
So it's a good.
Yeah, it's good. Yeah,
performance.
it's good. So, yeah, there's already room to.
So that's the end of today's session, and maybe we'll come back in 15 minutes, 10:55.是不是要准备开始？
你要我这样看起来。
Oh, let's start this session. Opponent should choose a question, choose a problem to challenge.
We challenge problem number 10, problem disclosure.
me yourself a challenge.
17 years after.
I would like to start my report. Okay, and I'm Ashley Wim from Team 910, and today I'm going to talk about the droplet explosion. here's my outline. First of all, we're going to talk about the problem statement, and we will talk about our observation video, then the theory that we used, then the experiment that we did, and in the end, we're going to talk about the conclusion. And here's the problem statement. When a drop of water mixture, for example, the water and alcohol, is deposited in the surface of hydrophobic liquid, for example, the vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. So we focus on, we're going to investigate the parameters that may affect the experimental results, and we're going to calculate the size of the final droplet. Okay, and here's our observation video. We can see the droplet just explore light this way, and this is our observation video by looking at this phenomenon. And let's talk about our theory part. And now let's first talk about the hydrophobic liquid. What is the hydrophobic liquid? It's used to trigger the fragmentation of the droplet and causes the phenomenon to happen, but it will not affect the later expansion. So this is just used to trigger the fragmentation of the droplet. And now let's talk about the surface tension. And it's also called the Marangoni effect of this phenomenon. And the Marangoni effect tells us that the fluid will with high surface tension will hold the other fluid with low surface tension in order to balance the tension on the interface. As like the picture shows, and the red line is referred to the force that causes by the different tension, and the inner circle is the lower surface tension, and the outer is the higher surface tension, so it will have a force by different kinds of surface tension. And now let's talk about the concentration of the solution. The alcohol has lower surface tension, and so it will just like make only effect. And the higher of alcohol concentration, the lower the surface tension is. And in a mixed solution of the alcohol and water, the Marangoni effect will be more bigger, when the difference in the surface tension between the center and the outer is larger. Like the picture shows in the last page, because of the difference of the surface tension, so the droplet made explosion on the surface of the oil that we used. And now let's talk about evaporation. So in a mixed solution of alcohol and water, the alcohol is easier to evaporate than the water because of it's just a trait of the alcohol. So the concentration of the alcohol will decrease. So like the mixture of the water and the alcohol. So and when the alcohol just evaporates, so the concentration of the alcohol will decrease because of the evaporation of the alcohol. And now let's talk about the thickness. And this is our model of the evaporation of the alcohol. Like the thinner liquid, like for example here, it's easier to have the evaporate because of the energy that's got is the same, and here is the have a bigger the energy have to separate in all this area, but here just a little bit. So this is more easier to evaporate because of the energy. And now let's talk about the model of our experiment. And when a water mixture droplet touches the surface of oil, like this shows, we drop a droplet on the surface of the oil, and this is the container. And the alcohol tends to spread on the whole surface in a short time, like the observation video we just seen. In a short time, so the water will spread a little because the flow that the solute gives. It's just like the water will pull each other to explore on this surface of the water in the container. And here's our model 2. And when the thin layer of alcohol evaporates, the rest of the liquid tends to fill in the hole. Like there's some space, the alcohol evaporates, so the water may just fall into the hole that's the alcohol evaporates, so it will turn to like a little droplet that we can see. and the mixture will then form into humps on the ring of the hose, which causes circular purling of the droplet air. So we will talk about what is the humps mean. So now let's talk about the form of a hump. And this is our model of a hump, and caused by the liquid flow and wetting. And what does this mean? We can see as this line, a balanced line of the liquid, and here's the hump. And evaporation creates the flow on the surface, which gives the mixture a force. So the extra mixture will be given an offset force to form the next hump in the linear purling thickness. So it's like when the alcohol just evaporates, and it will give a force to make the flow like in this way. So it will happen a hump like the picture shows. And here's the key factor of this experiment, and we're going to investigate list of these key factors of this phenomenon. And the first one is a hydrophobic liquid. And the use of the hydrophobic liquid is used to trigger the fragmentation on the surface of oil. And the surface tension is caused the Marangoni effect, and then we have said that because of the difference between the surface tension, so it will just explode on the surface of oil. And the concentration of the solution, how large the Marangoni effect will affect, that we are going to investigate. And the evaporation will change the concentrate. And the thickness we just told because of the energy that affect the evaporation rate. And here's our theory part. We're going to explain this phenomenon, and this phenomenon happens because different surface tension is center and outer. We have told in the and difference in the center and the outer concentrations causes different surface tensions, like the picture shows. And evaporation rate causes different concentration center and outer, so it will causes yes. And different thickness of the evaporation will be different, like the picture shows. Okay, and now let's go into our experiment part. Okay, first of all, we're going to talk about the parameters that we used. The first parameter is different kinds of alcohol, and the second parameter is the concentration of the water mixture, and we used ethanol for the alcohol, and we have 5 kinds of the solution of it, and the drop height of the droplet. We're going to investigate the effect of the drop height and the explore. And here's our experimental setup. This is our model, and the drop height, we have 5 different kinds of drop height, and we only use one droplet so that the amount of the droplet is all the same. So here's our focus point about the process of the fragmentation, and the max radius of the fragmentation is like the picture shows, and the size of the dots, we're going to calculate all the dots, and we're going to average them. And here's the radius of the final droplet that we investigate. And here's the different radius that we define. We define the radius as the inner ring radius, which was expanded to the maximum radius of their shrink. So they were shinked back like this, and we will explain why. And process of fragmentation like spreading is like the picture shows, the droplet spread out, and the radius of the droplet increases. So here's the process of the fragmentation too, and the radius of the droplets decrease because of the force that the surface tension gives, and the force that the molecule will pull each other, and it will turn to this way. And the process of the fragmentation is the final stage is like this. And now it's the experiment of different kinds of alcohol. And here's our alcohol varied, and we control the other things. And we can show that this can explore, but this can't explore. And now let's discussion about the alcohol varied. And the ethanol has a smaller surface tension, so different to water. So then it's protonal, and therefore ethanol solutes cannot successfully separate from onto the whole surface of the trigger. And the high surface tension different to the water, it's easy to have a more obvious phenomenon. And the experiment. And we're going to different kinds of concentration that we used. And here's our chart of the concentration varied, and we used the same drop height and the result is like the chart shows. And here's the concentration varied. In a high concentration varied, the size is the dot is smaller, and the concentration the other side it will be bigger. And let's discussion the discussion of the concentration varied. We know high concentration is have bigger radius since it's a bigger surface when different to water. So that is our result. And we're going to talk about high concentration make the dots more smaller, and the bigger surface tension difference to the water, so it can spread more easily. And the experiment of the drop height, then we can know the drop height also affect the radius of the droplet. So here's the discussion of the higher the height and the greater impact, so it will have the bigger impulse of the water, so the radius will be smaller. And here's our conclusion. The phenomenon is caused by the difference in surface tension between the water droplet and the liquid. So the surface tension of the water droplet needs to be small enough to produce an explosion. So higher drop will spread smaller because of we explain the impulse of the droplet. Okay. And here's the reference. And thank you for listening.
Thanks for the report. The first question I want to ask you is that I think that you only consider surface tension. Is there other forces or other things?
Of course, but I think the surface tension is the most causes of this experiment and this phenomenon because of the difference of the surface.
So, how do you control the concentration of the mixture? Like in your experiment, alcohol will evaporate. So
yes.
How do you control that 40% concentration of the alcohol, the mixture?
We just use we just mix the water and alcohol together in a different,
Okay. So what kinds of oil do you use?
Just the vegetable oil, like the product and sage.
So how often do you change the oil? Because after
every time, and we use the same oil that's by the same company. Yes.
Do you think the temperature will affect the phenomenon?
Yes, of course. Let's maybe a little maybe your parameters, but we are all in the same condition and the same environment. So we think this is not cause our experimental result.
Okay. Another thing. You use dropper or pipette or something to drop your mixture, right?
Yes.
Okay. So, do you think that each volume of each drop is the same?
Yes, we have controlled the amount of the droplet because we have just by one.
So
yes.
You dye the mixture, right?
Yes.
Okay. So do you think the dye will affect the concentration?
We just control that, so we don't have enough data. This is the dye effect, and we have shown the backup page, and it just make the video clear. So when we do our
so you did not use dyes in your experiment. Then how do you observe?
Just by the bright light. Just yes.
So. That means the videos are their own. to sacrifice my score for the ocean here. So maybe. Here I want to begin my opposition to work. Okay, so repeat the test again. When a drop of water mixture on the surface of a hydrophobic liquid, the resulting drop is sometimes fragmented into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. Oh, here's the structure of how the reporter solves the problem. First, they use the reason of fragmentation. Second, the type or concentration of water mixture. The third one is the size of the droplet. Okay, here are some pros and cons of the report. They use some theoretical model of literature and a simple, understandable qualitative explanation of the effect and appropriate use of media and graphs. But they lack explanation on graphs and a clear prediction of some phenomena and some parameters are missing. Okay. And about the theory, they use some relevant modeling or observing of the experiment detail and their own modification of the force and motion of droplets. But however, the cons are the unclear how modification of theory was actually formed and a sufficient model of force, tension, influences. These are some pros and cons about the experiments. They have an accurate and reproducible setup. Some conducted different parameters, but not all, include the key parameters. Okay. And no exact mention of theory and reality. No exact measurement of how the size of each droplet is, and theory are not experimentally verified. So here are some points I want to discuss about. Will the dyeing color affect the phenomena? Second, will temperature and other forces affect? And the third one is, at what range of concentration will this happen? The fourth thing is that, is there a limit of the dynamic viscosity of the oil so that it will not happen the phenomena? Okay. So I want to start the discussion now. Okay. So I want to use the blackboard here. The first thing is that this is the oil surface.
Yeah.
Okay. And do you think that the formation of each droplet will lead to different influences on this phenomena? I mean, like when you drop a droplet, it may deform like this, and this is the droplet. Do you think this will?
Yes, we control the same height and the same place that we drop the droplet. So we think this is the thing we do control. So we're not going to investigate this part.
Okay. The second question. Sorry. The second question is that how do you investigate the size of the droplet?
We investigate all the sizes with the droplet and we average it like the picture and like using this is how we measure the thickness of the droplet and how to measure the droplet.
Is there any data shown
Data because
about the droplet's size?
you mean all the data of the every droplet?
Here you said you average it. So
Yes.
about the data or graphs?
About the data? Yes. Of course. Wait. And here's the data of our radius of the inner droplet.
That's the radius. I mean the size of each fragmentation after the fragment size.
Yes, but we want to investigate is what the radius of the ring is, but not the droplet, the small droplet, how big it is.
Oh, right. Again, do you think the temperature will affect it? Because
Yes, of course, because of the evaporate, the rate of evaporate will change, so I think it will change, and I can improve my report by using different kind of temperature, and this may be the next parameters we are going to do.
all right. You said that surface tension is the most important thing in this phenomena.
Yes.
Do you think shear force is another parameter that could cause this?
Yes.
As a liquid, the shear force from here to here.
Can you explain why you think that will affect the experimental result?
Okay. When the droplet drops on the oil,
Yes.
it may cause shear stress on the two liquids.
Yes.
No.
Can you define what is the
Shear force. I mean,
Yes, yes.
shear stress is that the liquid will deform and deform like using it's not like a solid that it will deform.
Why do you think this is very important to our experiment? Because I think this we control in the same. Yes.
All right. So you said that you dye the mixture, right?
Yes. For just the observation video, because in the we have another way to see the observation of our experiment. So
just using natural light,
yes, we use bright light to shine on it, and we can see what's the droplet like.
Okay.
And we use the tracker to track the whole experiment phenomenon.
Okay. Between what range of the concentration of the mixture will this phenomena happen?
You mean?
I think in your data you show that about 30% of at least 30% of the
This one? Because we know that higher concentration have more alcohol in the water mixture, right? And alcohol may evaporate, so that causes many like the space that alcohol evaporates, so the water may come into the place that the alcohol evaporates, right? So it will affect the experimental result, and here's the experimental result that we saw. Oh, you mean
the least concentration of the mixture that can cause this phenomenon.
We used 30% of the concentration because lower than 30, we can't see this phenomenon very clearly. So
why?
Because of the surface tension, the difference of the surface tension is too small to investigate the phenomenon.
Do you have any theory, or you just use experiment to prove this?
Theory is like the Magoni effect.
Oh, all right. Do you think you can use other oils instead of you said you use just normal oil? Like
of course, we can use another kind of oil, and maybe we can investigate this kind of parameters. But we think the hydrophobic liquid is just for trigger the fragmentation. So it's not very important to use different kinds of oil to.
Will different oil affect the radius between the inner circle and the outer circle?
I think they may not affect the radius.
If a liquid, if an oil is dynamic, viscosity is very big. It's very hard for a liquid to float outside. Do you think there's a limit of dynamic viscosity, or?
I think it's about the surface tension because these two won't dissolve together. So I think it's just about the surface tension, but not the viscosity of the oil.
So you use alcohol, right?
Yes, right. And we have two kinds of alcohol that we use.
Two kinds.
Yes, as we shown in the experiment. Here we have two kinds of alcohol, but we shown that. Sorry about that. Where is it? This one can't explore, so we just use the other kind of alcohol to do the experiment. So we can't.
Okay. So.
Yes.
So why is the right side of that one can't explode?
Yes, I have said it here, and because of the smaller surface tension, so different to the water, so it's not able to explore, and that we can investigate the phenomenon.
So you said that at least 30% of the alcohol concentration, ethanol concentration is needed to observe the phenomenon.
Yes, that is our experimental result.
Okay. Do you think that the dissolve of alcohol will affect the phenomenon?
Because we have to let the alcohol evaporate, and it leads to this kind of phenomenon, so it's needed.
So
yes.
Okay. I want to ask. You mentioned the hump. The
yes.
hump. Do you have any picture or data of the hump?
We don't have calculate the hum because it's just a kind of how to say this, a kind of phenomenon, and this is why the phenomenon of how this experiment will happen. And here's our model that's just created by my team, and this is the demonstration of the hum. It's just like the picture shows. And we're not going to calculate it because we're not going to investigate the height of the hump or how it's going on.
I noticed in your presentation you mentioned the inner circle's radius will become bigger and then smaller, right?
Yes.
Then do you investigate the outer circle?
Of course, because we separate it to the inner circle and the outer circle because the inner circle will just like expand and just like post a small one, but the outer one won't move because this. So we define the outer one that the place don't move, but the inner circle is this will move.
Okay, move inside. Yes. Do you think that the outer circle, what's the maximum of the outer circle's radius? Do you investigate? I think in your data you mentioned the inner circle will become bigger and then smaller.
I think it's a good advice, and maybe we can do this this kind of parameters because we focus on the inner circle, but we didn't track the outer circle.
Okay, no.
Okay.
Please go to your graph about the inner circle's radius.
Concentration?
Yeah, this one.
This one? Okay.
So here, so it will become bigger and then smaller. Then why will it be a little bit like not irregular thing?
Because we have shown that in the observation video, because the first step pulled by the molecules just front like beside them, and it will pull together and becomes this kind of phenomenon, and then we investigate in our our observation video and also in our experiment.
Okay, that's the end of my question.
Thank you.
And here I want to summarize the discussion. First, I want to ask, in their video, they show that they die, but they said they use bright lights to observe the phenomenon, but I don't see the video. So I asked between what range of the concentration will the phenomenon happen. For the alcohol concentration, they said about 30%. The least concentration is about 30%. But for the oil dynamic viscosity or the density of the oil, they didn't mention. They said that's irrelevant. But I think that the oil should also change and consider its viscosity also. And I did not see the data of the size of the droplet. And for temperature, they said that it's an unimportant thing, but I do think that temperature will affect all the parameters in this.
Can you go to slide? Oh, my bad. Yeah, can you go to slide 6, please? Slide 6. Slide 6 says that the hydrophobic liquid is a trigger for the effect of happening. What do you mean by trigger? Does it cause?
Yes, it causes. If there's no hydrophobic liquid and this kind of
I think instead of causing, maybe you could say it's an interface of what happens. The hydrophobic liquid acts as an interface for it to spread out and is a facilitator of said phenomenon because the liquid will spread out over the interface.
Okay. What's your question about this?
Oh, I just wanted to point out how it's not a trigger, it's a facilitator.
Okay, I got it.
So do you have a quantitative theory in your presentation?
We use this
So do you
effect.
have like numbers that you can plug in and give us a result?
No, because this is just a phenomenon.
So you don't have a quantitative theory, you don't measure the parameters of temperature, the velocity of the particle, and the size of the particle. And
No.
this is slide 30, please.
We're just going to investigate what parameters will affect this kind of phenomenon.
Okay, thank you. And what about you? What do you what parameters do you think affect the experiment?
As I said, the temperature and the oil's dynamic viscosity, and also the ethanol itself. And in this experiment, instead of dyeing it, I think
Thank you. So on top of what you said, I think you should also recognize the velocity of the particle and the size of the particle. Okay, moving on. Could you go to slide 30, please?
30? Okay, this one.
Is this your only graph?
No, we have another graph.
Do you also have error bars in that graph?
We don't have the theoretical.
Okay, so no error bars, no error bars.
Yes.
Could you go to slide 21, please?
Okay, here's.
Okay, is this your own video?
Yes, it's just for observation, but not our experiment.
Okay, and simplify your experiment, you did not put food color.
Yes.
And you observed it without the food color.
Yes, we observed with the food color, but in our experiment we used the bright light to shine on
Okay,
it.
so when you collected your non-existent data, you didn't use food color.
Yes.
Okay. Do you have an idea of how, okay, that's a wrong question. So how do you think temperature and viscosity affects the phenomenon?
Okay, now for the viscosity part, if the oil is hard for the liquids to move out, then of course we can not easily observe the phenomenon. And for the temperature, if the temperature goes up, then like the alcohol will evaporate fast, and yes. And
thank you. Could you go to slide 19, please?
19? Yes. Here?
So you defined the radius of the dot by tracking the average particle, the droplet radius, right? The average. So do you think there's a large amount of error by taking the average of the droplets? Because it seems to differ quite a bit.
My time is up.
Okay, thank you. Hello, I'm Six. Okay. I'll be reviewing droplets. So that's a problem statement, you can read it yourself. And the main focuses are what parameters affect the fragmentation of the droplets and what are the sizes of the final droplets. So for the reported performance, they had an explanation of the phenomena, but no quantitative theory or a numerical parameter model to calculate it. For the experiment, they defined certain parts of the experiment and explained what happened, but didn't measure a lot of things, only measured the droplets. Some pros, they have demonstration videos, and they have some theory and some result and some conclusions. However, their experimental setup is sometimes unclear with the droplet size. They don't have any theoretical equations. The results are barely analyzed without any depth, and analysis is not discussed. And they don't explain the different results with the same conditions. And there's obviously no error bars in their single graph, and your increments are only 10%. Okay, and for the opponent, they summarized their presentation. They gave good pros and cons to discuss. They also asked relevant questions and considered viscosity, other parameters that they lacked in the presentation. However, they did not mention all the missed points, and they did not discuss the lack of numerical data or a quantitative theory, and they don't yet. So first I'm going to talk about the difference in hydrophobic liquid. The opponent said you should have tested other hydrophobic liquids, and the reporter said they only tested vegetable oil, and they observed a change, radius will change with other liquids, and they also said that the hydrophobic liquid acts as a trigger for said phenomenon. I agree with the opponent in the fact that you should have measured other forms of hydrophobic liquids to see its phenomenon. I agree that the radius will also change because of the different viscosities, but I think that the hydrophobic liquid acts as a facilitator or interface for said phenomenon to happen. They also talked about the food coloring's effects. Obviously, the opponent pointed out that food coloring would have an effect on the phenomenon, and the reporter said they didn't actually use food coloring in their experiment, only in the observation. I find that quite interesting because it would be very difficult to observe and actually track your data using a phenomenon without food coloring in it, and this affects the accuracy of your experiments. And they also we talked about the investigation of the size of particles, and the opponent considered individual particles, and the data of the average size of droplets was not present. And the reporter said individual size of the particles weren't tracked. The inner ring of the particle is important, not the size of the individual droplets. I agree with the opponent in the fact that you should be analyzing the size of the droplets because that was included in the problem statement, and that could also lead to deeper observations. Okay, and we also talked about the range of concentration. The opponent said you should have investigated the range of concentration, but the reporter did not investigate the range of concentration, allowing for the effect to occur. 30% was the lower limit due to the lack of surface tension. I agree with the opponent. You should have used a different varies of concentration of liquids, and you fail to suggest an upper limit to the phenomenon and when it will occur. And as for the temperature, the opponent said the reporter did not consider temperature in the experiment. And I agree with the opponent, you should always, when you're working with fluids, you should consider temperature, because the temperature will affect the viscosity and thus the phenomenon itself. So some points that you miss, both of you miss. So the temperature gradient wasn't really thoroughly explored, but the evaporation and that fluid depth was explored, which is good. However, and the role of the hydrophobic liquid as a interface or facilitator to the experiment was also not thoroughly explored. The size and the shape of the droplet as it hits the petri dish was also not talked about. And the velocity of the droplet was not talked about, even though you only talked about the height of the droplet, that should affect the velocity. And we could logically concur that the velocity should also have an effect on said phenomena. And also, the lack of theory was very much apparent, and it wasn't talked about as much as I wanted it to be. Thank you.
Okay, thank you for your opponent. And first, I'm going to clarify that droplet that we defined is the inner circle, and they also they just focus on the small droplet on the surface of oil. And here's the summary of the opponent. He has asked a question about consider surface tension. When we answered yes, and concentration will evaporate and make the dust went out, and the surface tension will change so that the radius increase. And the oil using that we think this is not very important, and the temperature effect. And yes, we think it's yes, but just a little bit. And we control the same temperature, so this is not the main process of our experiment. And if droplet is the same, we answer it yes. And we don't use full color, and we just investigate by the bright light, and it's easy to investigate under the bright light that shines on the surface of the oil. Here's the summary of the opponent, and he asked about a small droplet, and we just define the droplet as the in the circle, but it's not a small droplet on the surface of oil. And the temperature effect, and he asked this for many times, and the concentration and the viscosity effect, the alcohol will affect. We think viscosity is not the main causes of this experiment. And the summary of the reviewer, they say that we did not give the quantitative equations because of there's no we just explain this kind of phenomenon and should measure all the kinds of hydrophobic liquids. Then we can make use this kind of, and should investigate the droplet size and should do the temperature, and we agree that and it will be the nothing can improve. And the claim that we didn't say the temperature is irrelevant, and in fact we said it's maintain the same temperature and in the whole experiment. So this is I want to say, and thank you for listening.
It's time for jury to ask questions.
Okay, will temperature affect the surface tension?
We think yes, and because of the higher temperature will cause the alcohol more easier to evaporate.
You say yes, that's enough. But why didn't you consider it as one of the parameters to be
We
invested?
maintain the same temperature in all the experiments, so we think it may be another parameters to do in the future, like this.
I agree that temperature will be an effect on the. Sorry.
I think I understand your views. What about viscosity? You raised.
I mean, the viscosity of oil, for example, if the oil is it's very sticky, then
with that, the important in their investigation, which they just presented the way they presented how would the viscosity enter into the result.
like.
Which part of the result will be affected?
I know it. Viscosity will affect both the inner circle's radius and the outer circle's radius.
And not the rate of expansion of...
Also the rate of expansion.
So we all agree that they didn't use the dye, right?
My opinion is that using dye is very
No. Did they use dyes in their experiment?
They said no, but I think that it's very hard to observe.
So did you use dyes?
In our experience, no, but in the observation video, because we want to show everybody the fragmentation, so we're going to use the dye it's just for observation video, but not in our experiment.
May I add on to that point? I admire how you made it easier for us to observe, but I think when we're presenting our experimental processes, I think it's important to show us how you didn't put dye, because I don't remember there being any pictures of dye-less droplet explosions.
Yes, I think we may just put the setup on our presentation and will improve my report. Yes.
I have another way to observe the phenomenon without dyeing. Can I explain?
Nobody's asked questions, so you can just go. No, you can go ahead. we haven't used that.
Okay. So we can use a cell phone or a laptop or something like it's a screen and a flashlight, and under the oil, so the light will go up and the oil will become that specific color, and when we drop the droplet onto it, there will be different color between the two.
You can recommend that to the reporter.
Yes, sorry, but I think light is just a dot of the light, so it goes to the velocity of go to the whole container is not the same. So I think our experimental setup is more better than yours, because the light is just control all the environment to the bright light.
It's a screen of light, not just a screen.
It's for us to ask questions.
Okay.
Okay, I understand.
No, I think the statement of the problem asks you to investigate the size of the final droplet.
Yes.
What's your interpretation of that?
We define the final droplet as we just showed in the report.
The inner one or the rows which are formed on outer ring?
We define the inner ring as the droplet.
But I mean, that's your interpretation of the statement. That is the inner ring.
Yes, we define it the inner ring of the droplet.
Time is up.
Thank you.
So it's time for jury to give score. And the score for the reporters is 6, 7, 6, 6, 7. And now the score for opponent. 7, 7, 7, 7, 6. And And now it's the score for reviewer. 8, 7, 7, 8, 8.
老师能不能写一下？